So today we're starting chapter 9, which, as sad as this is, might be our last unit. Yep. I know. Okay, we don't have band. All right. Okay, so here's what we need to do then. We're going to talk about some stuff. It's fun and easy, but it is probably brand new. Some of it is very logical and some of it isn't. So let's just get our notes out. Here we go. Number 1, band. Benito Mitchell. Okay. Problem A. This unit is called combinatorics and probability. So the first thing we're going to do is figure out how many ways I can arrange 5 books on a shelf. So what are some thoughts? 5 books on a shelf. Yes, Kara.
You multiply 5 times 4 times...
Yes.
Okay.
Yes. So what, and I don't know if you've done that before, or if you know what you're talking about here. The idea is this. Here's my bookshelf. And there's room for 5 books on my shelf. Here are the 5 books I'm going to put on the shelf. So I'm just going to stand here and I'm going to reach into the pile and I'm going to grab one. Now I'm grabbing one book, but how many choices are there? 5. So I have 5 choices. That does not mean I'm putting 5 books there. That means I have 5 choices for that blank. Okay, so I grabbed one and put it there. Now I'm going to grab another one. How many choices do I have now? 4, and then 3, and 2, and 1. And those are multiplied. A big concept here, try to listen, is when you do this and that, you multiply. So notice, I am putting a book here, and a book here, and a book here, and a book here, and a book here. And when I'm doing this and this, I multiply. So all these numbers are being multiplied. Now, you can take your calculator out. This is going to be totally calculator dependent. You can take a calculator out and you can literally type 5 times 4 times 3 times 2 times 1. And that is not an issue. But what if I had 50 books to arrange on the shelf? That would be 50 times 49, okay, and that would, you could do it obviously, but it would take you a long time. So there is a notation, you may have seen it before, a notation for this concept. This is what we call, this right here, is what we call 5 factorial. This is the symbol for factorial. When you say 8 factorial, what you mean is start with 8 and then multiply every consecutive digit going down. So 8 factorial would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, luckily, your calculator will do this for you without having to, put in all the numbers. So go ahead and get your calculator out. Press math. Now, go across, press math, just a regular math button. Then go across the top till you get to probability, PRB. And in that column, do you see the exclamation point? Okay, so the way you do this, go back to the home screen. You have to put your number in first. So put 5 in first. And then math, prob, factorial. And it should say 120. So how many ways can I arrange 5 books on a shelf? 5 factorial. Now, I want you to look at question number 2. How many ways can I line 9 people up in a line? 9 factorial, who said that? Good job, Brayden. Here's the deal, folks. Is there any difference really between lining up 5 books on a shelf and lining up 9 people in a row? No. The general rule of thumb is, if you have n things, and you're lining them up in a row, it's n factorial. So it doesn't matter if it's people, books, teddy bears, it doesn't matter. If you're lining them up in a row, it's that factorial, okay?
So like on the test, for example, would the answer be 5 factorials or would it be
120,
Okay.
120. Now, as I'm talking about them, I'll often just state 9 factorial. You know how to type that in on your calculator, so we may not take class time to type them all in. You know how to do it on test day. You will write the answer. So what is 9 factorial? 362,880. Everybody okay with that? And that is actually the answer to the problem. The only work, so let's say this is the test, and you read that question, your work is probably going to be writing 9 factorial, and then in the answer blank, you're going to put down that number. That's it. There really isn't anything else to do. All right. How many ways can prizes be awarded for first, second, and third place in a race with 10 contestants? Okay, now stop and think about that for a minute. What are your thoughts?
Would it be 10 times 9 times 8?
Yes. She says, look, I'm giving away 3 prizes. How many possibilities are there for first place? 10. But somebody got first. So how many possibilities are there for second? Then 9, and then 8, and then we're done. Now that is not 10 factorial because it doesn't go all the way down. It only goes 10, 9, 8 because you're only giving away 3 prizes. So you're done. So that answer is what, 720? Okay, and again, this is going to be multiplied, guys. There will be times when we'll add, and we'll talk about that. But if you are giving away first and second and third, that's times. And is times. Okay. Mrs. Ford has 8 jumpers and 10 shirts. How many different outfits are possible?
10 times 9 times 8.
Now wait, stop thinking. Okay, you're me. Every morning, go to the closet. Got the shirts hanging here, got the jumpers hanging here, don't really care if anything matches. Just grab a shirt and grab a jumper. How many choices? I'm grabbing 2 things. I'm grabbing a shirt and a jumper. How many choices do I have for a shirt? 10 shirts. How many choices do I have for a jumper?
8.
Yeah. I'm picking a shirt and a jumper. The answer is 80. There's 80 different outfits. And if you think about it, that makes sense. Let's say I have, a yellow jumper and a blue jumper and a green jumper and da-da-da, okay? The yellow jumper could be paired with 10 different shirts. So isn't that 10 outfits right there with just the yellow jumper? And then there's 10 more for the blue jumper? Well, since there's 8 of these, you see how 80 just naturally comes out? So again, when you start saying 10 times 9 times 8 times 7, that would be how many ways can I arrange the jumpers in my closet? Because then I'm saying, okay, I got these 10 jumpers, I have to line them up. First spot in the closet, I have 10 choices. Do you see the difference? Yeah. I'm not arranging these, I am simply picking one. Mr. Ford has 5 sport coats, 12 shirts, and 10 pair of pants. How many outfits does he have? He goes to his closet, he has to pick a sport coat. How many options? 5. And he's gonna pick a shirt, and he's gonna pick a pair of pants. He has way more outfits than I do. He has 600. Okay, your keyboard has the home row where, you know, like you're typing, has those buttons. Those are the keys on the home row. Okay? Pretend I can pop them off and put them on in a different order. How many ways could I do that? 9 factorial. Guys, wouldn't I just be arranging 9 letters in a row? How many ways can you arrange n things in a row? N factorial. Okay, we already typed that one in. I can't remember what it is, but you know what 9 factorial is. Okay, how many ways can you answer 10 true-false questions? Think about that now. You sit down to take a quiz. There's 10 true-false questions. How many ways could you answer that? Meg?
90.
How did you get 90?
There's only 2 choices, and then 10 questions and 10 notes. And you can't go like all the way down factorial.
Okay, so you are so close. You're thinking about exactly the right thing. Okay, so here is the quiz. Question 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 questions. Meg says, I'm going to answer question number 1. I have 2 choices. And then I move on to question 2. How many choices? And then I move on to question 3. How many choices? So what am I going to end up doing here? What is my answer going to end up being? 2 times itself 10 times? Or 2 to the 10th? 2 to the 10th. You got 10 questions, you have 2 options for each. Now, what if this quiz were multiple choice, and it could be A, B, C? Then it would be 3 times 3 times 3 times 3, right? Remember, this is just like the books on the shelf. You have 2 choices. But since those 2 are separate than these 2, you still have 2 choices for this one, and this one, and this one, and this one. 2 to the 10. How many ways can 4 different prizes be given out if there are 10 people in the contest? So we have 10 of you, and 4 of you are going to get a prize. So somebody's going to get a marker, somebody's going to get a pen, somebody's going to get an eraser, and somebody's going to get a Post-it note. Okay, how many ways can I do that if there's 10 of you in here? What? That's exactly right. 10 times 9 times 8 times 7. And it stops. It stops because you only have 4 prizes to give away. 10 choices, 10 possibilities for me to give a prize to. You don't have something in your ear, do you? Somebody got the pencil. So now I'm going to give away my marker. I have 8 people, or 9 people left, and then 8 and then 7. Good, good, good. How many license plates are possible if they have to consist of 2 letters? So here's my license plate. It's got 2 letters and then 3 non-zero digits. A digit is a number, like 2, 5, 8. Those are digits. So I gotta have 2 letters followed by 3 non-zero digits. All right, here we go. License plate. I'm making the license plate. I have to put a letter here. How many choices do I have? 26. Okay. I have to put another letter. How many choices do I have? 26. Kids, is there any reason why the license plate couldn't have, I don't know, BB or LL? Is there any reason why that couldn't be? Absolutely none. It's perfectly okay. You can repeat your letters. Now, what happens next? A non-zero digit, which means 9 options, and 9 options, and 9 options. Are you starting to get the idea that when I set these blanks up here, it's options for that blank? How many options there are for that blank? Okay, well, I know you can type that in and get it. All right, number 10. Same license plate, but this time somebody has decided that nothing can repeat. Okay, so you make a license plate, but nothing can repeat. So how many options for our first letter? 26. How about for our second letter? 25, because you can't use the one you've already used. And then, and you're going to multiply them together. Okay, I'm the world's biggest Chuck Lofton fan, so every morning I watch WTHR News. That is called a call sign. That is a call sign, WTHR. All right? Now the question says, how many 4-letter call signs are possible if every letter is allowed? 26, 26, 26, 26, or 26 to the 4th power? What if you can't repeat? 26, 25, 24, 23. I don't want to go too fast, but does that make sense to everybody? If you can't repeat your letters? Go back to number 11. How many 4-letter call signs are possible, but you can't use vowels? So we have 4-letter call signs, but we can't use vowels. All right, now and these problems, we're not gonna do all the weird things. Normal. How many vowels are there normal? 5. A, E, I, O, U, right? No. A, E, I, O, U, okay? So if we're not allowed to use vowels, then there are how many options? 21. Now, we're going back to problem 11, which doesn't say anything about can't repeat, so we're just going to go with 21 all the way across. Then number 14 says all vowels, no vowels and can't repeat. So that would be 21, 20, 19, 18. All right, now we got a baseball team. How many batting orders are possible with your 9 starting players? 9 factorial. Kids, when you do a batting order, aren't you essentially just lining them up in order? Your first, your second, your third? So the answer is 9 factorial. 9 factorial. But what if the pitcher has to go last? What? So Peter's saying that's going to be 8 factorial. Now, I'll draw it up here in a second, but I want you to think about this. If here's my 9 players, okay, and I got to figure out a batting order. But I know my pitcher's going last. I'm going to grab him, and he's go stand over here. So how many kids am I really arranging? 8. I'm really putting 8 in order because he doesn't get to be in order. If you drew that out, if the pitcher has to go last, there's one option for that last spot. That's the pitcher. That leaves 8 kids. So I have 8 choices and then 7, 6, 5. 5. So do you see how that works out to be 8 factorial? 8 factorial. 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 How many are possible if the pitcher bats last and the best hitter bats third? 7 factorial. Because if I pull out these two, you're going last, you're going third, then how many people are left to arrange? 7. So 7 factorial. Good, good, good. How many 1-digit, 2-digit, or 3-digit numbers can be formed using the digits 1, 2, 3, 4, 5, 6? Now, it doesn't say anything about you can't repeat or anything, so don't read more into the problem than is there. They're just saying make some numbers that don't use 7, 8, or 9. That's basically what we're doing, okay? So how many 1-digit numbers are there if I'm only allowed to use 1, 2, 3, 4, 5, 6? 6. It's either 1, 2, 3, 4, 5, or 6, right? That's it. All right, what about 2-digit numbers? I have to use those 6 digits. So how many choices do I have here? 6. And how many choices do I have here? 6. So I could have the number 32, but I could also have the number 33. So there's 36 2-digit numbers.
What do you mean 32?
I'm picking a 2-digit number. So 32 would be an example of a 2-digit number. All right? Now what about 3-digit numbers? Wouldn't that be 216, 6 times 6 times 6? And then what? Add them up. There you go, guys. Here is our first addition. And the reason it's an addition is that we are creating 1-digit or 2 or 3. And an or problem means you have this many, this many, and this many. How many do you have all together? How many do you have all together? Well, whatever that is added up is what we've got. 258. So all together, there are that many options. Okay. So we got a long road ahead of us. We want to make sure we understand when we multiply and when we add. If you are picking a digit and a digit, you're going to multiply. If you have this many options, or this many, or this many, you're going to add. All right. Okay, got the word Chevy. How many 5-letter words can be formed from these letters? So in other words, how many ways can you rearrange those letters? They're not going to be real words. They're not going to be real words. 5 factorial. Because how many letters are there? 5. How many ways can you arrange 5 things in a row? 5 factorial. Easy. How about Precal? How many ways can you arrange those letters? 6 factorial. Because there's 6 of them. And again, to Kara's point, on test day, you're going to want to make sure you know how to type in 6 factorial and get 720 as your answer. Now I want to skip a couple. We'll come back and get them. But I want to skip down to number 23. Now I have the word precalculus. What is a little bit different about this word? There are repeating letters. Okay? When you have repeats, you have to deal with that, all right? So here's how it's done. It's very, very simple. Start with how many letters are there all together? When I wrote these out, how many letters are up here? 3, 6, 11 of them. You start with 11 factorial. That's the starting point. Then, you look through the word and say, hey, there's 2 C's. So we're gonna divide by 2 factorial, which is the 2 C's. And then, oh wait, there's 2 L's, so I'm gonna divide by another 2 factorial. Each repeated letter has to be handled on its own. So I have 2 C's, 2 L's, 2 U's. If I had 3 of something, this would be a 3 factorial. Is that all the repeats? Now, when you type this in on your calculator, and I want everybody to do this for me, you can type it in like this, but remember, anytime there's more than one thing in the denominator, you have to use parentheses. You aren't gonna get the right answer if you don't put that parentheses. So 11. I got 4,989,600. Anybody else get that? No? Okay, then I might be wrong.
I got that too.
Uh-oh. Majority rules. Just kidding. Try it again. No, I think that's right. All right, so while we're here, let's do Mississippi. So how many ways can we arrange these? Well, again, how many letters are there? I know I told you in the problem there's 11, but I probably won't do that, you know, another time. So just count up the letters. There's 11 of them. So we're going to start with 11 factorial, but some of them repeat. So it looks like, we've got 4 S's. So those are my S's. What else have I got? 4 I's. Whoa. My I's. And 2 P's. All right, let's see if we can get the right answer to this one. I got 34,650. All right, everybody got that concept? All right, back up to number 21. How many social security numbers are possible if anything goes? So no restrictions whatsoever. How many social security numbers could we make? Well, do you know what a social security number looks like?
No.
I hope you do, because you have one and it's an important number. So we've got what, 3, and then 2, and then 4, right? Now, I think probably in the real world there are some rules about social security numbers, but we're saying anything goes. So, how many digits are an option for this spot right here? 10. It says anything goes. So I can put a 10 here, or 10 options. I can pick a 1, a 0, a 3, a 6. I have 10 choices for that guy. What about this guy? 10. Isn't it 10 all the way down? Now, I really don't think there's anybody that has a social security number that's 0, 0, 0, 0, you know, but we're saying anything goes. These are all gonna be multiplied. So basically, that's what, $1 billion, isn't it? 10 to the 9th? Yes, Max?
Why is it 10 and not like 9?
Cause 0 counts. My social security number has 0 in it.
0 through 9. But wouldn't that be a 10?
Actually, mine has 2 zeros in
Wouldn't
it.
that be a 10?
What?
Wouldn't that be a 10?
I can't hear it.
Wouldn't it be its own digit?
It is.
Yeah.
So there are 10 digits. 0, 1, 2, 3.
Yes.
Okay. All right, so was this $1 billion? Is that what that was?
Yeah.
Okay. Now, I want you to think about this for a second. Is there a potential problem with our system of social security numbers? What'd you say? What if you get too many people? Exactly. There was some kind of scandal, I don't know how many years, I always feel like it was yesterday, but it was probably like 30 years ago, where, they were using dead people's social security numbers. And you might think, oh, what's the big deal? Well, there were some problems that came of that. So, let's suppose we ran out of social security numbers. What could they do? What? Well, I mean, you got 0 through 9, so we're not gonna do that. But what if we put a dash and put a couple more numbers on the end? Would that work? Yeah. Every time you do that, you increase it by 10 times, because you're timesing by 10, another 10. So that would be an option. And the reason I wanted you to think about that was this next question. How many telephone numbers are possible in the 317 area code? So I don't know about you, my phone number is 317, you know, okay? So everybody in the 317 area code is right there. So assuming, I don't think this is true either, but let's assume anything goes, wouldn't there be basically, what is that, 10 million?
Yeah, 10
So there's 10 million phone numbers in the 317 area code, all right? Well, they've already had to fix that because when this system was developed, like when I was a kid, my family of 7, 8, my family of 8 had one phone. So 8 of us had one phone. Now, that family of 8 has how many phones?
8.
At least 8. Some of my siblings have home phones too, right? So all of a sudden, when all this cell phone crap started, they ran out of phone numbers. Literally, they ran out of phone numbers. So what did they do? They created new area codes. They did that up north in Fort Wayne, and they did that down there in Bloomington. They created new area codes. So that you used to be 317, but now you're 812 or something, I'm making that up. And that's why now, you didn't used to have to put in your area code. If you were calling, if I was calling you, and you lived in my county, I won't do it, but if I were gonna call you, I didn't have to put in the area code that I had to do, because we can all live in the same county and have different area codes. Craziness, craziness, craziness. Okay, where am I now? Explain why at least 2 students must have the same first and last initial at Cathedral. So, here is your first initial and your second initial. Explain why there have to be duplicate first and last initials at Cathedral. Now that doesn't mean that there's another PM. It just means that somebody out there matches somebody else. How do I know that?
There's more students than there are combinations.
Bingo. If you think about first and last initial, if you count every possibility Aren't there just 26 times 26? I mean, isn't that it?
676, yeah.
So that's 676. So all of the combinations, and that includes things like QQ and ZX. I mean, this is every possible combination. And there's only 676 of them. Well, there's more kids than that at Cathedral, right? So somebody's gonna match. Does that make sense to you? I used to when I was a little kid, I would get so excited when I found someone that had my birthday. I just thought that was the coolest thing in the world. And then I realized when I got a little older that there's only 365 days in the year to have a birthday. And there's a whole bunch of people in the world, so obviously when I have my birthday, somebody is. All right, number 26, A and B. 2 questions. I need you to read both of them, A and B, and I need you to tell me if they are the same question, just worded differently. These are all gonna be word problems. So, are they the same question worded differently, or are they 2 different questions? 26, A and B, let's hear your thoughts. Both problems involve 20 people. In question A, we're picking 2 of them, president and vice president. In question B, we're picking 2 of them, governing council. What? Why?
Because in a governing council, there's more roles than just the president and vice president.
Well, there's only 2 people, so whatever jobs they're doing, I don't know. I think you're getting close.
Is it because, like, if there's 2 roles, one person can only do 1 role, right? And in the governing council, they can, like, you know what I mean?
Yep, I know exactly what you mean. Think about this for a minute, people. Suppose I walk in here and I say, I'm gonna pick a governing council. I'm gonna pick you, I'm gonna pick you. Would it matter if I picked her and then him, if they're just gonna be a governing council? Does it matter? No, there's no order in that problem. If I am picking them for the same job, governing council, committee, I don't care who gets picked first, they just wanna get picked. But if I walk in and say, you're president and you're vice president, that's different than if I say you're president and you're vice president, right? So when we have these 20 people and we're going to choose 2, the first question we need to get used to asking ourselves is, does order matter? Problems will vary. Does order matter? If order matters, and order matters when the jobs are different, president, vice president, that matters. When order matters, it's called a permutation. That's the math word for order matters. And in this problem, our notation would be 20P, and that P is for permutation, 2. This number right here is how many you have to pick from. This is how many you are picking. And the P tells me I'm picking in order. Order matters. If there is no order, then it's called a combination. And that would be 20C2. First number, 20 people to pick from. Second number, I'm picking 2. The C tells me order doesn't matter. All right? So, here's what I want you to do. I want you to press 20. I'm going to do this one first. I want you to press 20. Then I want you to go to where you found your factorial. And in that column, do you see an NPR and an NCR? So if we're doing this one, we're going to press our NPR button, and then we're going to put in our 2, and then we're gonna hit equals. You should have gotten 380. So put in the first number, then your P button, and then the second number, and you get 380. Now, order doesn't matter. 20, C button, 2, 20, C button 2. I got 190 for that one, did you?
Is it always like double?
No.
Same question?
No, that has to do with the fact that's a 2. That's what controls it. If that were a 3, that wouldn't be the case. All right, now I want to show you something. When order mattered, you can set it up like this. So I don't know, maybe some of you thought about that I have 20 choices for president and 19 choices for vice president. That will give you the same answer. If order doesn't matter, don't do this. Because the minute you do that, first, second, third, you put order into it. Okay, so you can't do that in a C problem, but you can do it in a P problem if you wish. Okay, next. I lost my paper. All right, let's look at number 27. A and B. Both problems involve, you got 13 people and you're picking 4. Both problems, that's what's going on. In problem A, am I choosing in order or is there no order in problem A? No order, so that's gonna be 13C4. But in problem B, there is order because president, vice president, different jobs. If it's different, if you're picking for different reasons, then you gotta use your P. All right, so 13 C4 is 715. And 13 P4, is 1,000 or 17,160. Okay. A. All right. Let's look at problem 28. Sydney's already got a guess. Anybody else have a guess? Oh, so did Peter, and he has the same guess. They both said 8 factorial. All right, I'm gonna shatter your hopes and dreams, okay? Here's what I want you to think about, and I'm not gonna do it with 8, because 8 is too big of a number for me to draw a picture of it. But I'd like you to think about having, maybe just 3 things to arrange. Now, we know that if we are arranging 3 things in a row, it's gonna be 3 factorial. So there are 6 ways that you can arrange 3 things in a row. I'll write them out, just so you can see what I'm talking about. These are the ways that you can arrange 3 things. I call them A, B, and C, and those are the 3 ways that you can arrange, or 6 ways, 6 ways you can arrange them in a row. Right? 3 things in a row, that's it, there's no other ways. Now, I'm gonna take these same things, they're A, B, C, and I'm gonna put them like in a circle. Now, there's only 3 of them, so it's not really gonna look like a circle, it's gonna look more like a triangle. But there's A, B, C. And then here would be A, C, B, and here would be B, C, A. Now remember, these are circular, they're in a circle now. They're around something. So B, A, C, C, CAB, and CBA. Now I want you to look at those for a minute. And I want you to tell me if you notice anything about them. These are circles now.
They're in the same order.
It- yeah, it's
rotated.
listed.
Someone used the word rotated. Yes, now they're not all exactly the same, but I want you to look at this one right here. Okay, see that one right there? And then I want you to look at this one right here. And I want you to look at this one right here. Those are all exactly the same order. No one has moved. Nobody has gotten up and moved. Like here, going from here to here, we had people get up and move. They switched seats. Here and here and here, I think. No, here, here, and here, nobody switched seats. What did we do? We just took our table and rotated it. When you put things in circles, since circles have no beginning and no end, there are fewer ways to arrange them because of the rotational aspect. Here's the general rule. If you're putting n things in a line, it's n factorial. If you're putting n things in a circle, it's n minus 1 factorial. So 8 people in a line is 8 factorial. 8 people in a circle is 7 factorial. 8 people in a line, 8 factorial. 8 people in a circle, 7 factorial. Because 8 of them repeat. We divide that 8, gives you 7 factorial. Okay, it's called a circular permutation. When you arrange things in a circle, it's 1 less factorial. Number 29. How many ways can 10 people be seated around a circular table? 9 factorial. All right. Now I'm going to blow your mind again. Look at number 30. Now it's starting to get a little more complicated. There's going to be a few more things we have to remember. So first of all, 6 keys on a key ring. I'm going to start by saying 5 factorial, right? On a circle, 5 factorial. Here's what I want you to think about though. So here are my keys, key A, B, C, D, E, okay? And I'm holding them up here, looking at them, there's my keys. Okay, well, what about this? I want you to think about those two. If I have my key ring in my hand, and this is the way the keys are arranged, okay? So you're looking at it, and that's what you see. What am I seeing? I'm seeing this, aren't I? Yeah, that's called a reflection. Now, so answer to the question is 5 factorial divided by 2. Because I can't count both of those because nothing's moved. I've just looked at it from the opposite side. Now, you don't do that very often, people. You have to be able, if you're going to divide by 2, reflections, you have to be able to look at it from both sides. So remember the people sitting around the campfire? 8 people around a campfire is 7 factorial. Don't be dividing that by 2 because you can't look at them from the other side. About the only things that we're going to have that reflection, that division by 2, are keychains, necklaces, bracelets, that's about it. Think about a necklace. Think about a necklace. You're seeing a necklace. If I pull it off, I'm seeing the same necklace backwards from you. So I'm going to divide that by 2. So if I had 10 beads on my necklace, it'd be 9 factorial divided by 2. When do I divide by 2? If it's something I can view from both sides. So those are called handheld circular permutations. I have a bracelet on my hand, I can flip it over and look at it from the other side. I have a keychain, I can flip it over and look at it from the other side. I have people at my dining room table, I cannot flip them over and look at them on the other side, right? So be careful. We don't always divide by 2. And we only divide by 2 if it's circular. If it's circular. Okay. All right, so let's start putting it all together. This is getting crazy, crazy complicated. We've done a lot today, so we'll do number 31 and then I'll stop. All right, here we go. How many necklaces can be made from one blue, one yellow, one green, one orange, one pink, and one purple? B. Okay, well this one's a lot easier than 32, but I promised I'd stop, so I will. But let's get this under control. How many necklaces can be made from 1, 2, 3, 4, 5, 6 beads? If the necklace has a clasp. Oh Lord. Versus if the necklace has no clasp. So I have 6 beads. And one question says clasp and the other question says no clasp. So I don't care, which one do you think you have an idea for? Anybody have an idea? Ed?
No class, just be 6 permutation divided by 2.
You mean 6 factorial?
Yeah.
Okay, actually, no clasp would be 5 factorial divided by 2. Because aren't we putting them in a circle?
Yeah, but if it doesn't have a class, can it go in a circle?
Oh, okay, you're getting way too technical. Pretend I have a string. I'm putting the beads on a string, and I'm gonna knot it. Okay? So now my beads are floating. Now, you know those little bracelets you make when you're a little kid and you have
Yeah.
a bead? Okay, that's what we're doing.
Okay.
So no class would be 5 factorial divided by 2. Alright, because there's 6 beads, I'm putting them in a circle. Now, what does a clasp do? It splits it, which means, remember all this, and I said these were the same? Well, not if the clasp is, if the clasp is staying put, then those are not the same. The clasp functions as another bead. Yes, it's another thing on the necklace. No, it's gonna be 6 factorial divided by 2. Another way to think about it, kids, for those of you that are kind of like, what in the heck? Okay, stop, wait a minute. Okay, my lanyard has no clasp, right? So it's a circle, right? But if I'm wearing a necklace that has a clasp, to take it off, what do I have to do? Oh my, and when I unhook it, what does it become? A line. So 6 beads on a line is 6 factorial. Got it? Yeah. Okay, now, if you, I don't know, you're all so excited to get out of here, but if you looked at the next problem,